Hi there, this is Heath. Welcome aboard. We're starting day 3, which is on combinations. But first, I want to correct something from the last video, and I apologize for this one. We looked at this example, 3.6 from the book, that described 36 people at a workshop. They're seated at 6 round tables. And I misread this as how many different seating arrangements are possible for the Morris family. But they're asking actually how many seating arrangements are possible at the entire table. And so we don't have to choose which table. We're assuming that we're just looking at their table. And so we're just looking at this one table with 6 places, and then we have to place their family. Let's space this out a little bit better. 1, 2, 3, 4, 5, 6. And so what I did last time was I placed the 3 family members, but then I didn't fill the remaining seats. And so what I did wrong is not fill the remaining seats. But I don't agree with Dr. Morris's answer either. What she says is that since the tables are round, it doesn't matter which specific seats they take. Because the table is round, there's no front or back or head or anything to the table. And in a purely abstract geometric sense, that might be true. But we're talking about people at an actual workshop that are sitting in an actual physical cafeteria or banquet hall or something somewhere. And it's entirely possible that at this round table, the person who's sitting here might have the sun in their eyes, and the person who's sitting here might be directly under the vent, and having cold air blasted on them the whole time. And the person who's sitting over here might be next to a couple at this other table that's a little bit too loud. In real life circumstances, even if the table is round, it does make a difference where you sit. And so I think this idea that using the fact that the shape is a circle would be true in a purely geometric context, but it's not true in a practical context. And so I disagree with Dr. Morris about this assertion here. Dr. Morris says that the 3 people's names are Joy, Dave, and Morris. No, Harmony. So if they sat here, that's identical to this, because this position can just be rotated into this position. But again, if each of these seats might have, an advantage or disadvantage based on how they are placed relative to other seats. And so I don't agree that these two seating arrangements are equivalent. And so I think this is a problem that could be stated a little bit better. So here's the solution I would recommend is choose a block of 3 seats. That happens in 6 ways. Then arrange the 3 people in that block. In that block. That's 3 factorial, which is also 6 ways. But then that's 3 of the people at the workshop. And so there are 33 people left in the workshop. So there are 33 choices to fill in this space then 32 choices to fill in this space, and then 31 choices to fill this space. So we fill the remaining spaces in 33 times 32 times 31 ways. And that's the step that I forgot to do last time. And so my answer is exactly 6 times higher than hers. So I would take this number and multiply it by 6. Because I think it does matter which seats they take at the table. And she says it doesn't. But like I said, if we had described this as an entirely geometric problem, placing, let's say, 3 stickers on a spinning disc, and since the disc is spinning, every sticker will be, at the top for the, top of the circle half the time for the same amount of time. That might be a case in which the order doesn't matter. But anyway, this is a problem in which the wording of the problem makes a difference, and we have a sort of a disagreement on how to interpret that question. But I definitely did it wrong last time, and I apologize for that. So I wanted to clarify that. Let's go ahead and move on to some other stuff. So one of the formulas we saw last time was this permutation formula, that if we have a set of n objects, the number of ways of selecting them where the order makes a difference is n factorial over n minus k factorial. As an example, in the last step here, we had 33 people, but we only needed to seat 3 of them. And so we took 33 factorial and divided by 33 minus 3 factorial. That's 33 times 32 times 31 times 30 times all the way down to 1 over just 30 times all the way down to 1. And all of these terms cancel. And this gives us the 33 times 32 times 31 that we get. For small numbers, I think this is just easy to do directly. But if n and k are both very large, and if you remember last time we talked about a problem involving choosing, several hundred cards from a Klingon deck of cards that was, also several hundred cards, I wouldn't want to have to write this out. And having this compact form is nice for a problem like that. Okay? So let's move on. What is a combination? So we're going to let n and k be integers with 0 less than or equal to k less than or equal to n. And we have a set of n objects, and they're all distinct. We can tell them apart from each other. We now take a subset of k objects, but we don't order them. It's an unordered subset of k objects. This is called a combination in S. Okay. Let's try an example. This is also an example from the Morris book. There are 10 athletes that are competing in a women's speed skating event. And we did a problem like this last time where we assigned medals to 3 of them. One of them was a gold medal, one of them was a silver medal, one of them was a bronze medal. This time we're not assigning the medals, we're just choosing 3 of them to form a committee to review the rules for future competitions. So the order in which we choose them doesn't make a difference in the committee that's formed. And so let's talk about how that changes the problem. In the original problem, we saw that there were 10 factorial over 7 factorial. That's 10 factorial over 10 minus, I'm sorry about that. Over 10 minus 3 factorial. That's where the 7 comes from. 10 factorial over 7 factorial ways of choosing 3 medal winners. But each different ordering of those players would be a different outcome. Having Tremors win gold and Kodaira win silver and Kataji win bronze is different from having Kodaira win gold and Takagi winning silver and Tremors winning bronze. In fact, for any set of 3 medal winners, There are 6 different ways of arranging those winners and matching them to medals. And so this includes every arrangement 6 different times, or every group of 3 6 times. And so the answer to Morris 3.2 should be 6 times greater than the answer to this question. And so we have to divide by 6, which turns out to be 3 factorial. And so there are 10 factorial in the numerator, and then 7 factorial and 3 factorial possible committees in the denominator. This gives us a combination formula. If we want the number of combinations, which are unordered, we calculate the number of ordered combinations. Permutations. That combinations, I mean permutations here. And then we divide by the number of orderings. The number of ways that we can arrange those k objects. So that's where the extra k factorial comes in from. This formula we abbreviate as, it's like a parentheses with an n on top and a k on the bottom, and we pronounce this n choose k. All right. This is theorem 3.11 on page 22, by the way, if you're following along the book. So let's look at this example. Jasmine is holding 3 cards from a deck of playing cards. She tells you that they are all hearts, and she's holding at least one of the 2 highest cards in the suit. If you wanted to list the possible sets of cards she might be holding, how long would your list be? Okay. So we have 3 cards. And they're all hearts. Well, the way of picking 3 cards that are all hearts, and I'm not worried about the ace and the king business yet. That would be, there are 13 hearts in the deck, and we have to choose 3 of them. So 3 and 10, these combine to give me 13, but this is what's in the denominator. That's the total number of ways of choosing 3 cards that are all hearts. Now, she says she's holding at least one of the 2 highest cards. She might be holding both of them. So I can't assume she's holding exactly one of these cards. So we could do 2 cases, or 3 cases. So the strategy now is we could do 3 cases where she's holding the ace but not the king. The case where she's holding the king but not the ace. And the case where she's holding the ace and the king. So let's look at that strategy. If she's holding the ace but not the king, then we know one of the cards for sure, and then there are 11 cards left she could choose from. There are 13 hearts in the deck, and the remaining 2 cards can't be the ace, and they can't be the king. So there are 11 more cards to choose from, and she has to choose 2 of them. So that's 11 choose 2. Plus the case where she's holding only the king, but not the ace. So then again, there's still 11 choose 2 ways of doing that. Plus, if we know that she's holding the ace and the king, then she only has to choose 1 card left, and there are 11 possible ways of doing that. And so this gets us 11 choose 2 plus 11 choose 2 plus 11 choose 1. All right, let's calculate that out for a moment. 11 choose 2 is 11 factorial over 2 factorial times 9 factorial. That's an 11 on the top. I apologize for that. 11 factorial and 9 factorial cancel and just leave me with 11 times 10, which is 110. But then I have to divide that by 2, and that gives me a 55. So then this next term is also a 55, 11 factorial over 2 factorial times 9 factorial. The third term is even easier to calculate. It's 11 factorial over 1 factorial times 10 factorial. And that's 11 factorial over 10 factorial. Every term cancels except for the 11. And then we divide that by 1, and we still get 11. And so get 55 plus 55 plus 11 is 121. So there are 121 possible sets of cards. Okay. But here's a second strategy we might try. What case is complementary to these three cases? The case where she holds neither the ace or the king. If we calculate how many cases have neither the ace nor the king and subtract them from the total number of cases, we should get the same answer. So in the strategy 2, all possible arrangements of 3 hearts is 13 choose 3. And then we're going to minus the arrangements with no ace or king. Well, the arrangements that have no ace and no king, that means there are only 11 cards to choose from, and all 3 cards have to be chosen from that set. So what do we get here? We get 13 factorial over 3 factorial times 10 factorial minus 11 factorial over 3 factorial times 8 factorial. 13 factorial over 10 factorial is 13 times 12 times 11. That's the 13 and the 10. Everything from the 10 down cancels, but I still have 3 factorial in the bottom to cancel, which is 6. 6 and 12 reduce and just leave me with 2 on the top. And 13 times 2 times 11 turns out to be 286. And then we're going to subtract 11 factorial over 3 factorial times 8 factorial. That's 11 times 10 times 9 over 6. And let's see, how much is this? 11 times 9 is 999, times 10 is 990. Divided by 6 is 165. And 286 minus 165 gives me the same answer, 121. And so either strategy works. We can start by building up cases. The case where we have an ace and not a king, the case where we have a king and not an ace, the case where we have an ace and a king. Or we can start from the top and subtract out the cases we don't want. Start with all of the arrangements of 3 hearts and subtract the arrangements that have no ace and no king. Both strategies, the additive strategy and the subtractive strategy, should get us to the right answer. And if you have time, you can do what I did here and try both strategies and verify that they get you the same answer. Okay? All right, let's try one more example. We have a deck of cards where 3 of them are red, 3 of them are blue, 3 of them are yellow, and 3 of them are green. We shuffle the deck and draw exactly 2 cards. So what is the number of ways that we can draw 2 cards of the same color? Okay. So if we look at the additive strategy, the cases would be 2 red cards plus 2 blue cards plus 2 yellow cards plus 2 green cards. And that would be, there are 3 red cards, so the way of choosing 2 of them would be 3 choose 2. Plus 3 choose 2. Plus 3 choose 2. Plus 3 choose 2. And that turns out to equal 12. The subtractive strategy in this case is much, much harder. There are a total of 3, 6, 9, 12 cards, which would be 12 choose 2. And then we'd have to minus all of the ways we could get 2 cards of different colors. So we would minus a red and a blue, which happens in 3 choose 1 times 3 choose 1. Choose 1 of the red cards and choose 1 of the blue cards. And then minus a red and a yellow card. Minus a red and a green card. Minus a blue and a yellow card. Minus a blue and a green card. And minus a yellow and a green card. This is a lot more work. This total number turns out to be 66. And is that right? 12 times 11. Choose 2. I'm messing up on this. What's going on here? This happens in 9 ways. This happens in 9 ways. This happens in 9 ways, and so on and so forth, which is a total of 54. And if we subtract 66 minus 54, we get 12. We're okay. I just thought I'd done something wrong for a moment. And so we get the same answer both ways, but I think it's much easier to do this as an additive problem instead of as a subtractive problem, because there are more cases that we have to check for this example. All right, let's move on. Talk about some combinatorial identities. If you're doing any kind of problems or solving problems or proving problems, you can substitute either of these expressions for one another because they're always equivalent. N choose k and n choose n minus k are always equal. For example, if we wanted to do 100 choose 96, that's the same as 100 choose 4. That 100 minus 96 is 4. These are the same. And the proof comes from the formula. N choose k is equal to n over k times n minus k factorials. And n over n minus k, n choose n minus k, would be n choose n factorial over n minus k factorial. And then n minus k factorial But n minus k, the n's cancel, and the minus and a minus become a positive. And so we get n minus k factorial and k factorial. And then these two things are equal to each other. So these two expressions are equal. I have not written that up in the form of a proof, but that's the idea. The formal proof would just be to assert that n choose k is equal to n factorial over k factorial times n minus k factorial, which is equal to n factorial over n minus k factorial times n minus k factorial times n minus k factorial over n times n minus k factorial times n minus k factorial, which is equal to n factorial over, no, not factorials anymore, n choose n minus k. So anytime you're working through a factorial and you think it might be easier to calculate with the smaller number instead of the larger number, you can switch it out. You're always allowed to do that. Let's look at the addition identity. I can split in a factorial into two smaller cases. For example, 18 choose 11. I can break down into 17 choose 11 plus 17 choose 10. That is, the number on the top of the combination goes down by 1. The number on the bottom of the combination stays the same in one place and then drops down by 1 in the other place. Let's proof this one and then we'll wrap up. The boring proof is just to work out the calculations. I'm going to start with the right side. N minus 1 factorial over k factorial plus n minus 1 factorial over k minus 1 factorial. I do this sometimes, bear with me. I start writing the factorials instead of the combination symbols, the binomial symbols here. N minus 1 choose k plus n minus 1 choose k minus 1. There we go. Now, that's equal to n minus 1 factorial over k factorial times n minus 1 minus k factorial plus n minus 1 factorial over k minus 1 factorial times, what's n minus 1 minus k minus 1? N minus 1 minus k minus 1 is n minus k, and then the 1's cancel. This is negative 1, and then this becomes minus a minus 1 becomes positive 1. And so then this just becomes n minus k factorial. I want to get a common denominator here. So on the left side, I need to make this n minus 1 minus k factorial into just n minus k. So factorial. So I need to multiply the first term here by n minus k over n minus k. So this is n minus 1 factorial times n minus k over k factorial times n minus k factorial. This goes all the way up to n minus k minus 1, but I've multiplied by n minus k, so now it goes all the way up to n minus k. Plus, this time I want to increase this from k minus 1 to k. So I'm going to multiply by k, n minus 1 factorial times k over k factorial times n minus k factorial. This goes up to k. It went up to k minus 1, but I just multiplied by k, so now it goes all the way up to k. And now these denominators are the same. That means I can combine these, and this is now n minus 1 factorial times n minus k plus k over k factorial times n minus k factorial. But n minus k plus k is just n, and n factorial times n, or I'm sorry, n minus 1 factorial times n is n factorial over k factorial times n minus k factorial. And that's n choose k. Now I said this was the boring proof. It's writing out the algebra, getting the common denominators, combining the terms. So let's talk about the funny hat proof. Let's say we have n objects. But we're going to replace one of the objects with a funny hat. So I've canceled one of the objects and replaced it with a funny hat. And now I have to choose k objects. So we're going to look at the additive way of doing this. The additive way of doing this would be the number of ways of choosing k objects, including the funny hat, or the number of ways of choosing k objects without including the funny hat, excluding the funny hat. Together, those should add up to all of the ways of choosing k objects. So if we choose k objects, including the funny hat, then we have the funny hat. And then what we have to do now is choose, I lost my pen again, here it is, k minus 1 remaining objects out of the remaining n minus 1 objects. I have n minus 1 objects left to choose, and I have to choose k minus 1 objects left. Plus, if I decide not to include the funny hat, then I have to choose all k objects out of this set, and there are only n minus 1 objects to choose from. And so that should give me the number of ways of choosing k objects. And so n choose k will equal to n minus 1 choose k, that's if we exclude the funny hat, plus n minus 1 choose k minus 1 if we include the funny hat. And so that's using an additive argument rather than using just pure algebra to do this. This is sometimes called an algebraic proof. And this is sometimes called a combinatorial proof. Combinatorial proofs are harder to do than algebraic proofs because you have to sort of be creative enough to see how to come up with the right combinations to make this work out. But when you come up with them, they're always turn out to be just shorter than algebraic proofs. They're clever and easy and kind of fun once you've seen a few of them. So we'll look at some more examples of combinatorial proofs in the near future. Not next time, but maybe the time after that. All right? Y'all take care. Have a great day.